reference if anybody needs this. So as we look at the second part, this area on page 662 is going to come in handy. Now, the equation that we want to focus on is going to be using the variables that were I should say, we were going to use as many variables that were a part of the original information as possible. Is there one of these equations that is that for us? Because our given variables for this problem were here, right at the top. So if I want to try to find the free length, I want to try to find or pick the equation that's I'm going to be able to use the most of these. Is there one of these equations that does that for me, or the rearrangement of? Go ahead. Yeah, the third one. So if we go down, this one right here uses the operating force and the operating length and our K factor. And then our unknown here is going to be that free length, right? So this is going to be the equation we want to focus on. So I'm going to rewrite that equation right here. And the variable I need to solve for is going to be my LF. So go ahead and solve for this, for LF in this equation. I'll rearrange mine here too. So by rearranging, you should get the operating force divided by the spring rate plus that operating length. Okay. So now we just have to plug in our values on the right side and we should get our free length. As I look at my value here, I get 1 1/4. Did my units work out? I've got my pounds canceled, but I've got per inch in the denominator, and then I added 0.83 inches. Can I add those together? Units wise? Can I do that? Yes, yes, we can. Remember, when it's a division in the denominator, and I'm dividing in the denominator, it's a multiplication times the top, okay? You guys were like, I think I can. Yes, you can. You can. So our units do come out. We can do that, okay? It's kind of like dividing by 1/2, right? It's a multiplication times 2, right? The 1/2 is in the bottom, the denominator of the denominator, and it's a multiplication up. So your units act the very same way. So it is inches plus inches. So 1¼ inches is going to be your free length, okay? Questions on that problem? Okay, all right. Okay, the next problem that we're going to be looking at is going to be problem 8 at the end of our chapter on page 689. What I'm going to do is I have to go underneath because the problem was a little bit longer than I wanted to really write all out. So I'm going to go underneath my camera here. And as we look at problem number 8, it says the following data is known about a spring. So this is kind of like, here we've got a spring and we can measure some things about it. And now we want to try to figure out other things about it. Okay, like its working characteristics. So we've got 19 coils on a spring. They're squared and ground ends. The outside diameter is measured at 0.56 inches. The wire diameter is 0.059 and corresponds to a 25 gauge music wire. The free length is 4.22 inches. And what they want us to calculate for this spring is the spring index. That's going to be that C, capital C, the pitch, lowercase p, the pitch angle, and the solid length. Okay. So what I want you to do is I want you to take, I'm going to give you 5 minutes. So just start kind of devising your plan for determining each one of those based on the information that you're given. Okay. So, so I'll give you 5 minutes and then we'll resume. Okay, let's just start looking at it. Even if you didn't get through all of it, that's totally okay. But we'll start looking at computing, in this case, the spring index. The spring index is that capital C. I'm gonna zoom out for a little bit. And you're gonna find, or tell me, where do you find that equation for the spring index? You guys have it handy? 662. Okay, 662. So at the top of page 662, here's that spring index, and it's going to be the mean diameter divided by the wire diameter, right? The wire diameter. Now, this is the one where they recommend having a value of 5 or greater. Otherwise, it's going to be wound too tight and you could start to see cracking on the wire diameter if it gets too close. Okay. So if you want it to be a smaller, like inside diameter, for instance, then you want to be sure that you're using either smaller wire and trying to get around that so that you don't exceed that. So to go underneath, whoopsie, I'm going to go underneath. And what I did was I wrote out that equation. Now, because we're not given the mean diameter in our given information, we need to calculate it. So we need to take the outside diameter and subtract the wire diameter to get that mean diameter. And then we're going to divide that by the wire diameter. So we're going to take 0.560 inches minus 0.059 inches. That'll give me my mean diameter on top. And I'm going to divide it by the 0.059 inches on the bottom. So what do we get for a value for C? .49. Yep, 8.492. I get that. I'm gonna put the 2 in there. And these would be inches canceling out, right? So this is just a factor. All right, no units here for C. No units for C. Okay, any questions on that one? So that's the first part. We've got that one done. Now we need to determine what the pitch is. Okay, the pitch. That's our next variable that we have to find. So did anybody get that far and find the equation for pitch that you would use? Like where would it be located? Or what page is it on in our book? 662. Yep. So it's kind of in the middle-ish here, right? Now it's not a pitch is equal to, but we have some information here so that we can rearrange it to solve for pitch, right? This gives the relationship here with free length and number of coils and such. So we were given in our problem that our spring is ground and squared, or squared and ground, right? So that means that on this top one right here, this is the equation that we're going to use, okay? So we're going to take LF is equal to the pitch, which is going to be our unknown, times the active number of coils, we'll talk about that in a bit, plus 2 times dW. Okay, so I'm going to write that out first. So LF is equal to, the pitch is what I'm going to be solving for, NA plus 2 times W or dW, which is our wire diameter. Now, LF is going to be our free length, so we have that as a given. P is going to be our pitch that we're going to solve for. And then they have NA. NA is the number of active coils, the number of active coils. We're given the total number of coils, okay? Now, total number, the number of active coils in the paragraph just above here, okay? The number of active coils when we have squared and ground ends is going to be N minus 2, N minus 2. For plain ends, it's going to be the number of coils, and for plain ends, but they're just ground, is going to be N minus 1. Because we're squared and ground, we're going to be N minus 2. Okay, N minus 2. And if you want to get a pictorial of what those look like, as a reminder, on the bottom of page 658, the ground and squared ends are this figure right here. Okay, right there. So they ensure that it's going to be nice and flat at the bottom, but because of that grinding away, now we're losing some active coils that are gonna be part of the operation. So NA is going to be N minus 2. Okay, so I'm going to put a little where NA is equal to N minus 2. So we'll put that value in there in just a little bit. So let's rearrange so that we solve for our pitch. Okay, so we have everything known here except for our pitch. So go ahead and rearrange this equation to solve for pitch. Once you have it rearranged, go ahead and put your values in with units, and take a peek up here if you just want to confirm the rearrangement, so that put your units in so that we can, make sure that we have the appropriate units in the end. We're looking for pitch. So yeah.
Why is it NA equal to minus 2? Like it says here, for plain coils with ground ends, NA equals N minus 1.
Right, this is ground and squared. So if you look just above there, ground and squared, ground ends or simply squared, each one of the coils is, there's two inactive, so it's gonna be n minus two. Squared and ground ends is n minus two. Squared and ground ends or simply squared, each one of the coils is inactive and the number of active squares is n minus two. It's in the paragraph above. Does that make sense? Okay. Yep, so because it's both, we have to do minus two. So you should end up with a pitch of 0.241. Now, you'll notice that coils are in the bottom here. I crossed it out. It doesn't technically cross out, but the units for pitch are always inches. Even though we're using the coils, it kind of gets it down to the unit measure. So coils, you wouldn't write it inches per coil because it's not per coil. It's the distance between from one coil to the next. Okay. So, so the coils just drop out and we're going to leave it at inches. Okay. So any questions? Did everybody get 0.241? 0.241. Okay. All right. So that takes care of our pitch. We've got that done. Now we're going to calculate the pitch angle. Okay. The pitch angle is right below in that on that same page at the bottom of the second column. Our equation is going to be lambda is equal to the inverse tan times that pitch divided by pi times the mean diameter. So go ahead, and this is a plug and chug. It's going to be a direct equation. Put it on the back here. So this is going to be my step 3, I guess. Okay. So my lambda is equal to tan to the -1 or the inverse tan times, make sure that you always write your equation in variable form first before you put your values in. Okay, that lets me know like what you're going to do before you do it. I forget, you guys have like not had me for like, well, most of you had me for kinematics. You guys had me. Yeah. Now, as we look at this pitch angle, if you read down in that section, and it's just above the illustration and the equation, it says here that for practical purposes, the pitch angle should be less than 12 degrees. Okay, that's just a recommendation of. So most of them you're going to see that are less than 12 degrees. The stresses get higher when it's anything above that. So again, it doesn't mean that it can't, but you're kind of adversely, affecting the end result of the operation if you go above. Okay, so so recommendation below 12, and when we calculated hours, we're at 8.72. Okay, 8.72. So that's good. It's good. So that means that we have the pitch angle. Did everybody get the same value as I did? Yeah. Okay. All right. Number 4. Solid length. Okay. Solid length. Okay. Did anybody get this far to solve for the solid length? Yeah. What'd you get?
Yeah,
Yep. 1.12. And what did you use to get it?
figure solid length means coils times the diameter of the light.
You got it. And that's not given in the book. That is not given as an actual equation in the book. So if you were kind of going around and trying to use the K factor and using the solid length, you have too many unknowns each time, right? Too many unknowns. So exactly what BJ did, well, let's think about it. If the solid length is when everything collapses, and if you know how many coils there are, there's 19, right? And you know how thick the wire is, 0.059, you multiply those two together, there's your solid length. There's your solid length. So that's what that one is. Not in the book, not in the book, but you kind of get at it thinking about it. So so LS in this case is going to be using that data that we were given. So we're going to take the number of coils, 19, times the diameter of the wire. Okay. So N times DW, make sure you write that out for me. So that's going to be 19 times 0.059 inches. And again, yes, it's coils would be the units there, but it's just really a unit we're multiplying by how many times. So LS is going to be 1.12 inches. There you go. That one was a little sneaky, I thought, but you got it. You got it. Okay, so if we go back to the front, that's our fourth part and our final part of problem number 8. Any questions on this one at all at this point? Okay, then let's move to problem number 9. It's a continuation of, so I'm going to go back underneath and we're going to look to our next slide. Okay. Now our next slide is going to build on this very same problem. And we want to compute, though, the force to reduce the length to 3 inches. Okay, the force to reduce the length to 3 inches. And then what would the stress be satisfactory for average service? So we're gonna have to calculate the torsional shear stress, and then we're gonna have to compare it to the design stress. Okay, so go ahead and try to devise a plan to answer the first question first and then the second question. Okay, I'm going to give you again 5 minutes to kind of peruse through and jot down some notes. So using that equation 8.6 on page 667, okay, the equation that I'm referring to is at the bottom of the first column. Like right there, this one right here. So we're going to be looking at, you could use either versions. I'm going to look at the first one here because it has the deflection in it right there. And we have all of the variables. So I'm going to use this version here. You could use that one if you wanted to. We did calculate the C, so it makes it a little bit shorter. So either one, but this is the deflection. The deflection is how far that spring, has moved. It's going to be that difference from whatever a value is. So we're going to use that free length to the 3-inch dimension. That's going to be our deflection. And then capital F is going to be the force to get to that point. So it's going to be like an operating force. The mean diameter, we know what that is. 8 is just a constant. And A is going to be our active coil. So it's going to be the 17, which is 19 minus 2. G is going to be our shear modulus. I'll show you how we know what that value is. And then dW to the 4th is going to be our wire diameter. Okay. So let's find G. Okay. Find G because we know really everything else. But G is the one that's like, what? So if we go back in the problem, it gave us the size of our wire was 0.059 diameter. Okay, they didn't tell us if it was music wire. They didn't tell us the kind of steel or anything like that. But if we look on table 18.2, which is the standard diameters for the wire in spring, there's a couple different columns here. Okay, we know that our diameter is 0.05 and it's connected to a gauge, a 25 gauge. Okay, so if we go down our first column on that page 660, it doesn't go to 59, but on the second page, I'm sorry, 25, right? 25, not 59, 0.059, 25 gauge. So 25 gauge is on the page 661. Okay. I want to give anybody motion sickness. Here's 25 gauge. And if we go over the 0.059 is in the music wire column. Okay. That's the material. It's music wire. So zoom out here. Now we're going to go to the table where the shear moduluses are. And the shear moduluses are found on page 668. And here is where we have materials and their shear modulus and their tensile modulus. The tensile modulus we're not worried about. We want to know what the shear modulus is. And here is our music wire, 11.85 times 10 to the 6th PSI. Okay, so again, they didn't give it to us, but we had to find it on the chart to determine that it was music wire. And now the music wire has this as the G. So now knowing this, now we have everything that we need in order to solve for our capital F in that equation. So let's go ahead and do that. Let's rearrange to solve for capital F. Now I'm going to point a lot and then I'm going to write it. So as we look here, we want to get F by itself on the right-hand side of the equation. It's in the numerator, so that's good. That's helpful. So I'm simply going to multiply G up on the other side, our DW or our wire diameter to the 4th on the other side. And then I'm going to divide by 8, divide by the mean squared, and then divide by the number of active coils. Okay. So my equation comes out to be F is equal to, and I'm going to call that the operating length or the operating force is going to be our deflection at the operating length. And we'll expand that out in just a little bit. It's going to be the free length minus the 3 times G times DW. And that's going to be to the 4th, right? Divided by 8 then DW squared, and then NA, right? And NA. So now we're going to plug in our values. We're going to plug in our values. So put it on this side. I know that my deflection is going to be my free length. So I'll put those variables above. It's going to be the 4.22 inches minus 3 inches. So this is going to be my free length minus my operating length. Okay, the distance that they want us to go down to. Times our G. That's going to be the 11.85. 11.85 times 10 to the 6th PSI. Okay. I've got to do pounds per square inch. Times my wire diameter, right? My wire diameter to the 4th, 0.059 inches, parentheses, to the 4th. Divided by 8 times my wire diameter squared, 0.059 inches. I'll do this, do the symbol so it's consistent top to bottom. And that's going to be squared times 17 coils, the active number of coils. Now you can go ahead and you can plug that all in, or you can take my word for it. Okay. So these 2 inches squared and those 2 inches squared are going to get rid of the inches to the 4th. Okay.
Hey Kelly, shouldn't like the overall shouldn't that be cubed instead of squared?
Cubed. Did I copy it wrong?
The equation that I'm looking at has like the wire diameter is to the 4th, and the other one, the other diameter is cubed.
Is it cubed? Yeah, maybe I copied it wrong. I'm sorry. Let me go take a peek. It is cubed. Thank you. Thank you. Thank you. So this should be underneath here. Sorry. That was me. Thank you for catching that, Hunter. So yeah. Yes. Oh my goodness. Gosh, it was going so good. All right. So this is, that's going to be my 8 times, that's going to be my 0.059 0.56 inches minus 0.059. That's what it is. Does that look better? And my cubed went down, you're right, it's the mean diameter. So then we have to take the 0.56 minus the wire diameter cubed. Thank you. So getting back to the units here, just making sure. So I need, these inches are gonna cancel out with this one. And the only thing I don't have canceled out is the pounds on the top, which is good because I'm looking for a force, right? Does everybody follow the units? This is 1. This is squared underneath here, so that's going to take care of one of those. So then underneath here, this one would take care of one of those, so that would be 3. And then it would take care of the cubed underneath. Okay. And pounds are left over. So my force operating by going through that, if you want to, you can, and double check me, please. It's probably a good idea. You should get 10.25 pounds. 10.25 pounds. Did anybody confirm that number? Yeah, you did. Okay. Yeah, I know I did it earlier and yeah. Okay, so now this is my force operating. This is my force operating. So that was the first part of this problem number 9. I'm going to now use that force operating to determine what my operating shear stress is going to be. Okay, what my operating shear stress is going to be. So if I go back up to the top here, what I want to find, I have my operating stress done. So my second part here is going to be, I need to determine what my shear stress is. So to find the shear stress, did you guys find that one? That one is on the previous page, 666. And there's 2 versions here. The one on the right uses the C, the spring index, and the one on the left doesn't. Let's use the one on the right. It's a little bit cleaner without as many powers to deal with. So we're going to use this one. It's going to be the 8K times F times C divided by pi divided by dW squared. So it's going to be equal to 8K times F. And this is going to be our operating force that we just calculated times our mean diameter divided by pi divided by the wire diameter squared. Oh, I know I'm doing that wrong. C, I'm using the second one. So it's the 8K FC divided by pi dW squared. So each one of those values then, we already know. So we know 8 times our K value. We calculated the K value in, oh, we didn't calculate the K value yet. Oh, we get to calculate the K value. So what's the K value again? The capital K, that's not the spring rate. Lowercase k is the spring rate. Capital K is the wall factor, So the wall factor is just above on page 667. It's right here. Okay, right there. There's the wall factor. So got to figure that out. So I'm going to down here, I'm going to say K wall factor is equal to, so capital K, not lowercase k, 4C minus 1 divided by 4C minus 4 plus 0.615 divided by C equals 4 times C. We did do C in our first problem. We found C to be, in problem 8, 8.492. 8.492. Minus 1 divided by 4 times 8.492 minus 4. Our C value is unitless, just so you know, plus 0.615 divided by 8.492. 8.42. So I'll double check. Our K factor is 1.17. 1.17. Just want a quick confirmation. Did anybody else get that value? 1.17. Did you get that, BJ? BJ did. Okay, good. Good, good, good. Now we're going to use this value up in our stress equation, and then we know everything else. So that's going to be 8 times 1.17. The K factor, there's no units, times the force that we just calculated, 10.25 pounds, times our C, 8.492, divided by pi, divided by that DW 0.059, the wire diameter, right? Not the mean, not that I'm looking at this wrong. No, it's the wire diameter. And, oops, I have inches in there. Inches squared. Inches squared. So units wise, on the top we have pounds, and on the bottom we have inches squared. So it makes sense that for stress, it's going to be pounds per square inch, right? So tau then, our shear stress should be 75,500, and you can write PSI here. You don't have to put pounds per square inch, so PSI. And that's going to be, I'm going to call it O, that's going to be like our operating shear stress, which goes along with the operating length and the operating force, right? Operating shear strength. Now, the problem didn't ask us what the operating shear stress was. It asked us what? It asked, would the stress be satisfactory for average service? Okay. Now we got to look. Okay. So if this is our operating stress of 75,500 PSI, we've got to find what the design stress is. So the design stress is going to come from those 6 little charts starting on page 664 to 666. And what we need to do is we need to find our material. Now remember, our material was music wire. And on page 668, we use the G of 11.85 times 10 to the 6. So this is A 228. A 228. So we want to find the chart where we say A 228. So on those previous pages there, hopefully, at the top of page 665, right here is A 228. And it says music wire, right? So now we want to find our wire diameter, 0.059, and we're going to go up to the average service line and then over to the left to find the design stress, the allowable stress. So 0.059, 0.05 or 0.06. It's really darn close. So I'm going to go up the 0.06 line just to the slightly to the left, and it actually crosses right here. And we're going to go over, okay? And it looks like we're right at about 130, right? 130. So if we look, our design stress is equal to 130,000 PSI. So our operating stress is less than our design stress, right? Our operating stress is less than our design stress. So are we okay? We are. We are. The design stress is what this is allowable, right? Like how much stress can this take? And our stress is much lower, much lower. So we're going to say this is okay. This is okay. Okay. So that's answering that question. So I'll go back down to see if anybody needs to kind of just double check your answers here. So this was like a two-part. We had to calculate our K value, that wall factor first, and then use it in this equation, and then find our allowable based on the chart and the material that we have. Okay, so this is then the end of problem number 9. Okay, and as I said, 8 and 9 are the lead into a couple of your homework problems, okay, that you're going to continue with this information. So make sure that you keep this handy and the values that we've gotten here, because these are all confirmed numbers. Okay. All right, so we have one more example problem or practice problem to do. And that is going to be, I'm going to go back underneath. That is going to be our design case study. Now, this is going to be an in-class example that Ryan is going to lead for us because he created this one for us based on, again, another, a design project that he worked on. And he'll kind of explain it and go through the process. So what I'm going to do, though, is I'm going to make this one a separate video by itself. So I'm going to stop here, but I'm going to start another video right after.